Have you ever, sat down and wondered, how can your brain, a physical thing, right, made of cells and chemicals and stuff, how can it create the feeling of consciousness?
It really is a mystery.
Yeah.
One that's puzzled philosophers and scientists for centuries.
Yeah. What if the answer to this puzzle, what if the answer lies in the strange world of quantum mechanics?
Now, that's a fascinating possibility. There's a theory out there. It's called quantum consciousness. And it suggests exactly that quantum mechanics is somehow involved.
Okay, so quantum consciousness, let's unpack that. But first, can we, take a step back? For those who might not be familiar with quantum physics, what makes it so different from the physics we learned in high school?
Sure, so classical physics, the kind of physics that describes the everyday world, the motion of planets and baseballs and all that, that's based on the idea that the universe is deterministic, like a giant clockwork mechanism.
Right. Cause and effect, everything's predictable.
Exactly. If you know the initial conditions, you can predict the outcome with perfect accuracy. But quantum mechanics throws a wrench into that neat picture.
Okay, so how does it do that?
Well, the term quantum itself refers to discrete packets of energy, the smallest possible unit of energy, like a tiny, indivisible chunk. It's not continuous.
Okay, so you can't have half a quantum.
Right. It's all or nothing. And this leads to some very peculiar phenomena. For example, quantum entities can behave as both waves and particles.
Waves and particles.
Yeah, depending on how we observe them. It's called wave-particle duality.
So it's like they have a split personality.
Kind of, yeah. It's like they're not quite one or the other until we look at them. Then there's quantum superposition, where an object can exist in multiple states at the same time.
Multiple states at the same time. That sounds pretty wild.
It is. It's like that coin spinning in the air. It's both heads and tails until it lands. And only when we measure it, when we observe it, does it collapse into a single state.
Okay, I'm starting to see where the weirdness comes in.
It is weird, but it's been experimentally verified. It's one of the most well-tested theories in all of science.
Okay, so how did scientists go from these strange quantum behaviors to something as complex as human consciousness? How did those two things get linked?
It's a long and winding road. But I guess it started with a fundamental question about free will.
Free will?
Yeah. If the universe operates like a predictable machine, as classical physics suggests, then how can we have genuine choice? Where does free will fit in?
I see. So quantum mechanics maybe provides a way out of that deterministic trap.
Exactly. Quantum randomness introduced an element of unpredictability, a way for free will to potentially exist within a universe governed by physical laws.
So it's not a perfectly predictable game of billiards after all, more like a roll of the dice, where the outcome is uncertain.
A very good analogy. And while quantum consciousness doesn't aim to replace neurobiology, it does suggest that quantum mechanics might play a role in explaining subjective experience. You know how we feel, think, and perceive the world?
Okay, so it's not just about neurons firing?
Right. There might be a deeper quantum level at play, a level that we're only just beginning to understand.
So are there any specific theories about how this might work? About how quantum mechanics could be involved in consciousness?
Yeah, there are actually several. One that has gained a lot of attention is called orchestrated objective reduction.
Orchestrated objective reduction?
Yeah, orch for short. It was developed by physicist Roger Penrose and anesthesiologist Stuart Hameroff.
Orch or R? Okay, tell me more. How does it work?
Well, Orch suggests that tiny structures inside our brain cells called microtubules could be the stage for quantum processes. Think of microtubules as like the scaffolding inside cells. They provide structure and support. But Penrose and Hameroff proposed that they might also act as the brain's quantum computers.
Hold on. We have miniature quantum computers inside our brains.
It sounds like science fiction, right? But it's a serious proposal. Penrose theorized that quantum superpositions in space-time could collapse due to a gravitational threshold. And when this collapse happens, this objective reduction, it gives rise to conscious moments.
Okay, so we have microtubules maybe doing quantum computations. Then gravity comes into play, collapsing these superpositions, and boom, we have a conscious experience.
You got it. That's the essence of it. And Hameroff added the orchestration part. He proposed that the signals coming from our synapses, the connections between neurons, they actually orchestrate the quantum computations happening in these microtubules. It's like they're conducting the quantum symphony.
So it's like a grand symphony. The microtubules are the instruments, quantum physics is the sheet music, and our synapses are the conductor shaping the experience. That's a beautiful picture. But there's a major hurdle here, isn't there? Quantum phenomena are incredibly delicate. They usually show up in highly controlled, extremely cold environments. Our brains are anything but that.
That's right. That's one of the biggest criticisms of orch. How can these fragile quantum effects survive in the warm, wet, and chaotic environment of the brain? It's a valid concern.
So are there any real-world examples of quantum effects happening in warm biological systems?
There are, actually. Photosynthesis, the process by which plants convert sunlight into energy. Recent research suggests that plants might be harnessing quantum coherence to optimize energy transfer during photosynthesis, and this all happens at regular temperatures.
Plants using quantum mechanics to make food. That's pretty mind-blowing.
It is, and it lends credence to the idea that quantum effects might be more pervasive in biology than we previously thought.
Okay, so maybe it's not so outlandish to think that quantum processes could be happening in the brain, even if it's a noisy place. But where does consciousness come in? How do we go from quantum events to the subjective experience of being aware?
Well, that's the million-dollar question, isn't it? And one that researchers are still trying to figure out. But orch proposes that the collapse of quantum superpositions in microtubules orchestrated by synaptic inputs is what gives rise to conscious moments.
So each collapse is like a tiny spark of consciousness.
You could think of it that way. It's a bit like a strobe light, where each flash illuminates a moment of conscious awareness. It really is a fascinating way to think about it. But one of the most mind-boggling aspects of order is the potential connection between consciousness and gravity.
Okay, I have to admit, the idea of gravity playing a role in our conscious experience is pretty wild. How does that work? Like, what's the connection?
So, Penrose's theory of objective reduction proposes that quantum superpositions collapse due to a threshold related to gravity. It's as if gravity acts as a sort of cosmic referee, deciding when these quantum states choose a definite outcome.
So gravity is somehow involved in collapsing the wave function, bringing those quantum possibilities into a single reality, and that's what we experience as a conscious moment.
That's the essence of it, yeah. And this connection between gravity and consciousness has some pretty profound implications.
Like what? Give me an example.
Well, for one, it suggests that consciousness might not be solely an emergent property of complex brains. It could be a fundamental aspect of the universe itself, woven into the fabric of reality alongside space and time.
Wow. That's a huge shift in perspective. It's like saying consciousness isn't just something that pops up when matter becomes complex enough, but rather it's always been there, a fundamental ingredient of the cosmos.
Precisely. And if that's the case, it opens up a whole new world of possibilities for understanding the nature of reality and our place within it.
Okay, my mind is officially doing somersaults.
Mm-hmm.
But if orch or R is correct, wouldn't that have implications for our understanding of free will as well? We talked earlier about quantum randomness providing a loophole for free will in a deterministic universe.
Absolutely. If gravity is involved in collapsing the wave function and that collapse is linked to consciousness, then our conscious intentions might actually influence those quantum choices.
Hold on. Are you saying that we're not just along for the ride? That our choices, our intentions, could be influencing the collapse of these quantum superpositions? And that's what creates our unique experience of the world.
That's the proposition. It's a radical idea, but it suggests that our minds aren't just passive observers. We might actually have a hand in shaping the reality we experience. Of course, this raises a whole host of new questions about how this influence works, what the limits of that influence might be, and how we can reconcile this with our understanding of the laws of physics.
It seems like every answer in this field just leads to more questions. But how do we even begin to test these mind-boggling ideas? It's not like we can just crack open someone's skull and observe quantum processes happening in real time.
Right. We can't directly observe these quantum events, but we can look for their footprints, their effects on the larger scale of brain activity.
So like searching for clues, trying to piece together the puzzle based on the evidence we can gather.
Exactly. One promising avenue is to use brain imaging techniques like fMRI and EEG to search for patterns of brain activity that are difficult or impossible to explain using classical models of brain function.
So we're looking for anomalies, deviations from the expected behavior that might hint at something quantum going on behind the scenes.
Precisely. If we see, for example, long-range correlations between different brain regions that happen faster than classical signaling would allow, that could be a sign of quantum entanglement at play.
Those nearly instantaneous synchronizations we talked about earlier.
Yes, those are prime examples. Another area of interest is exploring how anesthesia works. We know that certain anesthetic agents can switch off consciousness, but exactly how they do that at the molecular level is still a bit of a mystery.
But couldn't anesthetics be working on a purely classical level by interfering with neural pathways or neurotransmitter activity without invoking any quantum effects? How do we disentangle those possibilities?
That's a great question, and it highlights the challenge of proving a quantum connection. One way to address this is to look for specific effects that are predicted by quantum theories, but not by classical models.
So we need to design experiments that can tease apart those quantum fingerprints from the background noise of classical brain activity.
Exactly. And there have been some intriguing findings. For example, certain studies using EEG have shown patterns of brain activity during conscious perception that seem to correlate with the theoretical predictions of orch or R, particularly the idea of a beat frequency that corresponds to conscious moments.
Hang on, beat frequency. Could you back up a bit and remind me what that refers to? I'm getting lost in the quantum weeds here.
Of course. So first, it's important to understand that brainwave frequencies are patterns of electrical activity in the brain that can be measured with EEG. Different frequencies are associated with different mental states like sleep relaxation or focused attention. Or proposes that these brainwave frequencies might arise from the different energy states of quantum superpositions in microtubules. And when these superpositions collapse, the transition between those energy states could produce a specific beat frequency that correlates with conscious awareness.
So it's like each conscious moment has its own unique quantum signature, a specific frequency that we can potentially detect.
That's the idea. And while these findings are still preliminary and need further investigation, they offer a tantalizing glimpse into the possibility that quantum processes might be contributing to the symphony of brain activity that underlies our conscious experience.
I have to admit, the idea that our thoughts and feelings might be orchestrated by quantum events is both awe-inspiring and a bit intimidating. It's like realizing that the universe is far stranger and more wondrous than we ever imagined.
I agree. It challenges us to expand our understanding of what's possible and to embrace the mystery of our own existence.
But haven't these findings been met with skepticism? I imagine not everyone in the scientific community is on board with the idea of quantum consciousness.
Of course, whenever you're dealing with a paradigm-shifting ideal like this, there's bound to be healthy skepticism. Some critics argue that the brain is simply too warm and wet for delicate quantum effects to play a significant role. Others point out that we still don't fully understand how classical brain activity gives rise to consciousness. So, invoking quantum mechanics might be premature.
So it's a debate that's still very much alive and kicking.
Absolutely. And that's a good thing. It forces proponents of quantum consciousness to refine their theories, design more rigorous experiments, and address the legitimate concerns of their critics.
So it's a constant back and forth, a process of refinement and testing that hopefully pushes us closer to the truth.
Exactly. And while brain imaging is a valuable tool, there are other experimental approaches that can complement these findings and perhaps provide more direct evidence.
So how do scientists actually test these mind-blowing ideas beyond looking at brain scans? What other methods are they using?
Well, one approach is to design behavioral experiments that tap into cognitive processes that might be particularly sensitive to quantum effects. For example, decision-making under uncertainty, or tasks that involve ambiguous perceptions.
So situations where our brains have to grapple with multiple possibilities, where the outcome isn't clear-cut.
Precisely. In these kinds of tasks, classical models often struggle to explain the nuances of human behavior, but quantum models, with their inherent probabilistic nature and ability to represent superpositions of states, might provide a better fit for the experimental data.
So are you saying that our minds might be using quantum tricks to navigate the uncertainties of the world?
It's a possibility, and there have been some interesting studies that suggest human decision-making might exhibit features of quantum superposition and entanglement. For instance, some experiments have shown violations of classical probability laws in decision-making tasks, suggesting that something non-classical might be at play.
That's fascinating. But how do we know that these violations aren't just due to some other factor, some quirk in human psychology that we haven't accounted for?
That's a crucial point. It's essential to rule out alternative explanations and to ensure that the experimental design is rigorous enough to isolate the potential quantum effects. And that's why replication is so important in science. If these findings can be consistently replicated across different labs and using different experimental paradigms, it strengthens the case for a quantum influence.
It seems like we're still in the early stages of exploring these ideas, but the potential implications are profound. If it turns out that our minds are truly tapping into the quantum realm, it could revolutionize our understanding of consciousness, free will, and even the nature of reality itself.
I completely agree. It's a journey of exploration that's full of challenges, but the rewards could be immense.
Well, before we get too carried away with these mind-bending possibilities, maybe we should take a step back and consider some of the other approaches to understanding the mind-matter connection. We've focused a lot on orch or R, but there are other theories out there that offer different perspectives.
Absolutely. Orch is just one piece of the puzzle. There are other quantum brain approaches, like the work of Harumi Umezawa, who applied the framework of quantum field theory to brain processes.
Quantum field theory, that sounds pretty heavy duty.
It is. It's a step beyond standard quantum mechanics, dealing with systems with infinitely many degrees of freedom.
Infinitely many degrees of freedom. You've lost me again. Could you break that down a bit?
Sure. Degrees of freedom basically refer to the number of ways a system can change or move. Think of a single pendulum swinging back and forth. It has 1 degree of freedom. Now imagine a complex system like the brain, with billions of neurons interacting with each other. The number of possible ways that system can change is incredibly vast, essentially infinite.
Okay, I'm starting to get the picture.
Yeah.
So how does quantum field theory apply to the brain?
Umezawa's theory elegantly describes how classical neural activity might emerge from these complex quantum interactions. It's like a school of fish. Individually, their movements might seem random, but collectively, they form these beautiful synchronized patterns.
Ah, so individual neurons firing could be like those fish. And Umezawa's theory explains how their collective behavior gives rise to large-scale brain activity that we can observe with techniques like EEG.
Yes. And the beauty of quantum field theory is that it can account for the long-range correlations and coherence observed in brain activity.
So it's like zooming out to see the bigger picture, moving from individual neurons to the intricate dance of the whole brain.
Precisely. And by incorporating concepts like dissipation, the loss of energy over time, and chaos, this theory offers a more nuanced view of how the brain might be processing information at the quantum level.
So it's not just about isolated quantum events, but how those events interact and influence each other over time and across different areas of the brain.
Yes. It's about understanding the dynamic interplay of quantum processes within the complex network of the brain. And there's another intriguing approach that focuses on what happens at the synapse, the tiny gap between neurons where information is transmitted. Physicist Henry Stapp has proposed a model where the act of conscious choice might influence the quantum state of neurotransmitters as they cross the synapse.
So our intentions could be affecting the behavior of these chemical messengers in our brains.
That's the idea. It draws on the idea of quantum state reduction, where the act of observation or measurement influences the state of a quantum system. Stapp suggests that conscious choice, in a sense, acts as the observer in this scenario, influencing the fate of these neurotransmitters.
It's like our minds are reaching down into the quantum realm and nudging those tiny particles along a certain path.
It's a powerful image. And while this model is still very much under development, it offers a fascinating way to connect conscious intention to physical processes in the brain.
It seems like we're only just beginning to scratch the surface of what might be possible when we consider the intersection of quantum mechanics and consciousness.
I agree, it's a field that's ripe for exploration, and I'm excited to see what discoveries lie ahead.
Me too. But I think we need to take a breather here. My brain is starting to feel like it's in superposition, trying to process all these mind-bending concepts at once. We've covered a lot of ground, from the basics of quantum physics to the intricacies of orch and other quantum brain approaches. What I'm really curious about is how these ideas might translate into real-world applications. Is there any way to move beyond speculation and into the realm of empirical evidence?
That's a great question, and one that researchers are actively grappling with. There are a number of experimental approaches being explored to see if we can catch these quantum culprits in action.
Well, I'm all ears. How are scientists actually trying to find evidence for quantum consciousness in the brain?
Well, one promising area involves using techniques from quantum information theory to study the brain. This means applying concepts like quantum entanglement and quantum computing to understand how the brain might be processing information.
So we're trying to decipher the brain's code, but using the language of quantum information instead of classical bits and bytes.
Exactly. Quantum information theory has opened up entirely new ways of thinking about how information can be encoded, transmitted, and processed, particularly in systems that exhibit quantum properties. And researchers are starting to apply these tools to the brain.
It makes sense. If quantum processes are happening in the brain, they would probably be involved in information processing too, right?
Right. And one of the most fascinating ideas in this area is the idea of quantum error correction codes in the brain.
Error correction codes, what are those? And why would the brain need them?
Think about any information processing system. Your computer, your phone, even a simple radio. Errors are inevitable. Data can get corrupted during transmission or storage.
Like when you get static on a phone call or a file gets corrupted on your computer.
Precisely. Error correction codes are ways of protecting information from these errors. They involve adding redundant information to the message so that even if some parts get lost or corrupted, the original message can still be recovered.
So it's like sending multiple copies of a letter just in case one gets lost in the mail.
That's a good analogy. But what's remarkable is that quantum information theory has revealed entirely new ways of doing error correction that are far more powerful and efficient than anything possible with classical methods.
Okay, I see where you're going with this. Are you suggesting that the brain might be using these quantum error correction codes to protect the information it processes?
That's the hypothesis. It's still very speculative, but there are some intriguing theoretical models that suggest how this could work. And if it turns out to be true, it would be a major breakthrough in our understanding of how the brain works.
It would definitely add another layer of evidence to the idea that the brain is a quantum machine, wouldn't it?
Absolutely. It would suggest that the brain isn't just using quantum mechanics passively, but is actively exploiting its unique properties to optimize its information processing capabilities.
But how do we test this experimentally? It seems incredibly challenging to peer into the brain at that level of detail and see if these quantum error correction codes are actually operating.
It is a challenge. It requires developing new experimental techniques that can probe the brain's information processing at the quantum level.
I imagine it's like trying to listen in on a conversation between subatomic particles.
That's a great way to put it. But scientists are resourceful, and I'm confident that they will find ways to address these challenges. The history of science is full of examples where seemingly impossible measurements became possible with the development of new tools and techniques.
Well, it's certainly an exciting time to be studying the brain and the mysteries of consciousness.
It really is. We're living in an era where the boundaries between different fields of science are blurring, and new collaborations are leading to unexpected breakthroughs. The quest to understand quantum consciousness is a perfect example of this interdisciplinary spirit.
And even if it turns out that quantum mechanics isn't the ultimate answer to the riddle of consciousness, I have a feeling that this exploration will yield profound insights into the workings of the brain, the nature of reality.
I share that sentiment. Sometimes the journey of discovery is just as important as the destination.
Well, on that note, I think we've covered a lot of ground today. From the theoretical foundations of quantum consciousness to the experimental challenges of testing these ideas. My understanding of the brain and the universe has been thoroughly shaken and stirred. Any parting thoughts for our listeners as they continue to ponder these mysteries?
Sure. If your listeners want a fitting soundtrack to their contemplations, I suggest checking out the song Vices by Slayer.
Vices by Slayer. Keep those brains buzzing.